We will begin with semiconductor theory. In your training, you learned that electrical current is actually nothing more than a flow of electrons. The question is, where do these electrons come from and how do they move through the wire? To answer this question, we must first examine the atom. All solid material is composed of minuscule particles called atoms. Depending upon the atomic structure of the atom, this material can be anything. The atoms are held together by a force referred to as a bond. There are three types of atomic bonds: ionic, metallic, and covalent. Ionic bonds are commonly found in insulator materials. Metallic bonding occurs in conductor materials, and covalent bonding occurs in semiconductor materials. Here you see the atomic structure of a silicon atom. Silicon is a common material used in the production of semiconductor devices. In its pure form, silicon is referred to as an intrinsic material. Notice that the silicon atom has 4 electrons in its valence shell. The valence shell is the outermost orbital path that an electron can travel around the nucleus. Electrons contained in the valence shell require the least amount of energy to be knocked away from their orbital path. The maximum number of electrons which can exist in the valence shell is 8. Now you see the silicon atom as it would appear in a piece of silicon material. Notice that when the silicon atoms are bonded together to form the material, they share valence electrons. As you can see, in its pure form, the silicon material already has 8 electrons in its valence shell. Basically, the material acts like an insulator because it can neither accept nor easily emit electrons from its outer shell. Before pure silicon material can be used as a conductor, it must be doped with impurities. One type of impurity will provide the silicon material with an excess of electrons. These are called free electrons. Another type of impurity will provide the silicon material with a shortage of electrons in the valence shell. These are called holes. The doped material with the excess or free electrons is called the N material, and the doped material with the deficiency of electrons or holes is called the P material. When the semiconductor materials are joined together, some of the electrons from the N material flow into the P material and fill the holes that were created in the P material when it was doped. This new area, which is now void of charge carriers, is called the depletion region. It is this depletion region which makes it possible to control semiconductor devices. The device we just formed is called a diode. It contains a cathode and an anode. Notice that the N material forms the cathode and the P material forms the anode. The function of the diode is to allow current to flow in one direction only. Notice that when the negative side of the power source is attached to the N material and the positive side of the power source is attached to the P material, the depletion region disappears. The reason for this is simple. The negative side of the power source emits electrons. Since like charges repel, and the N material is already full of electrons, then the electrons coming from the negative side of the power source will force the electrons forward toward the p-n junction. In the same respect, when the positive side of the power source is attached to the P material, the holes in the material are forced away from the source of power and toward the p-n junction. Since the holes in the P material are basically places where electrons could exist, and the holes are an inherent part of the P material, then the holes cannot leave the P material. However, the free electrons being forced to the p-n junction can leave the N material and travel into the P material. As the electrons cross the p-n junction, they are pulled toward the positive side of the power source. This results in a current flow through the diode. Now notice what happens when the diode is reverse biased. Watch the area of the depletion region. You will see the depletion region expand when a positive potential is placed on the cathode and a negative potential is placed on the anode. This is due to the fact that the majority charge carriers in the N material are attracted to the positive potential of the power source, and the majority charge carriers in the P material are attracted to the negative potential of the power source. Therefore, when the majority charge carriers are pulled away from the p-n junction, the depletion region widens, thereby causing the diode to turn off. Here you see the diode being operated from an alternating current source. Notice that the diode can actually turn on and allow current to flow, or it can turn off and stop the current from flowing. It is this forward bias and reverse bias principle which allows semiconductor devices to function. Actually, it all boils down to like charged particles repelling one another and unlike charged particles attracting one another. If you can understand how the diode works, you can understand how any semiconductor device works. The next solid-state device we will examine is the bipolar junction transistor. BJTs are available in two semiconductor configurations, PNP and NPN. Bipolar transistors are considered as a current amplifying device. This is due to the fact that a small base current can control a much larger collector current. In servo amplifier circuits, the BJT may be operated as a switch or as an amplifier, depending upon the control circuitry. Here you see the NPN bipolar junction transistor. Notice the arrow on the lead labeled emitter is pointing away from the base of the transistor. Much like the symbol of the diode, the current flow into the emitter is against the direction of the arrow. The base section of the transistor is actually very narrow and lightly doped. The collector and emitter, on the other hand, are doped very heavily. This results in the depletion region from both end materials extending deep into the base section of the transistor. Notice that when a positive bias voltage is applied to the base terminal with respect to the emitter, the depletion region between the base and emitter disappears. This is due to the fact that the PN junction between the base and emitter is now forward biased. Now notice what happens when we place a more positive voltage on the collector with respect to the base. The depletion region between the base and collector actually widens. This is due to the fact that the PN junction between the base and collector is now reverse biased. Since the collector now has the larger positive potential, the base collector junction will respond in the same way as if the base had a negative potential applied. Also, the larger collector voltage will attract the majority charge carriers away from the PN junction. Since the base section is lightly doped, there will be fewer majority charge carriers available to recombine with the charge carriers coming from the emitter section. As a result, about 95% of the emitter's charge carriers will pass through the base section and flow into the collector of the device. The collector voltage will then pull the electrons through the end material toward the positive side of the power source. Here you see the NPN transistor being used as an amplifying device. Basically, a small positive voltage at the base will control the current flow between the emitter and collector. As the base voltage increases, the resistance of the transistor decreases, thereby causing less voltage to be dropped across the transistor and more voltage to be dropped across the load resistor labeled RL. When the resistance of the transistor decreases due to the forward bias condition between the emitter to base junction, the current flow through the transistor will actually increase. For this reason, bipolar junction transistors are commonly labeled as current amplifying devices. Here you see 4 NPN transistors being used as switching devices. Notice that by controlling the on-off condition of 2 NPN devices at the same time, we can make the current flow through the motor reverse directions, thereby causing the DC motor to run forward or reverse. When a transistor is used as a switch, it is typically operated in its cutoff mode and its saturation mode. In the cutoff mode, no current flows. In the saturation mode, the transistor conducts maximum current. The next device we shall examine is the junction field effect transistor. This device is often referred to as simply a JFET. The junction field effect transistor is constructed of a bar section of one type of semiconductor material sandwiched between 2 sections of the other semiconductor material. The 3 leads on the JFET are labeled gate, drain, and source. Here you see 2 types of bipolar JFET devices. One is an N channel and the other is a P channel. The bar of semiconductor material sandwiched between the gate sections is referred to as the channel. The ends of the channel are designated as the drain and source. The gates of the JFET device are doped heavier than is the channel bar. This causes the depletion region to penetrate deep into the channel when the FET device is reverse biased. The name field effect was derived from the fact that the depletion regions in the channel are the result of electrostatic fields generated by a reverse bias at the gate channel junctions. When the reverse bias condition is increased sufficiently, the electrostatic fields meet in the center of the channel, thereby causing the current flow to stop. This is often referred to as pinch-off. The gate channel PN junction is seldom operated in a forward bias condition. It is almost always operated in a reverse bias mode. This allows the FET device to have a very high input impedance. Also, the gates of the JFET will draw virtually no current. Notice in this animation, the gates of the JFET are not receiving a voltage. The only voltage which is applied to the device is placed on the source and drain leads. Unlike the bipolar junction transistor you just examined, the JFET does not require a bias voltage to allow current to flow. Instead, the JFET requires a bias voltage to control or stop the current flow. In some respects, the JFET operates much like a vacuum tube in that it must be biased to reduce or stop its current flow. Amplification of the JFET device is made possible by increasing and decreasing the reverse bias condition of the gate-to-channel junctions. As you can see, the drain current is controlled by the width of the channel between the gates. As the reverse bias is increased, the electrostatic fields created by the gates also increase. This results in the channel becoming narrower. The JFET device can also be operated as a solid-state switching device. Removing the bias from the gates allows the JFET to conduct maximum current. Applying a large reverse bias causes the electrostatic field to pinch off the channel, thereby causing the current to stop flowing. Due to their high input impedance and low gate current characteristics, FET devices are used extensively in electronic control circuits. Here you see the symbol of an N-channel insulated gate metal oxide semiconductor field effect transistor being illustrated in the enhancement mode. Insulated gate FET devices like this one are commonly used in the output stage of some servo controllers. Notice that the construction of the insulated gate MOSFET is considerably different from the junction field effect transistor you just examined. This FET device gets its name from the fact that the gate lead is insulated from the channel material. A thin layer of silicon oxide is used as the insulator. Notice that the source and drain leads are attached to blocks of N material fused inside the solid block of P material. The gate lead, as you should have noticed, is attached to a small metal plate mounted on top of the insulated material. In effect, the gate is insulated from the semiconductor material. Now let's see how this device works. As you can see, if the gate terminal does not have a bias voltage applied, the transistor will not conduct. When the gate terminal is made positive with respect to the source terminal, negative charge carriers will be pulled from the N material and induced into the P material block. As the positive bias on the gate is increased, the channel created by the electrostatic field from the positive bias causes more negative charge carriers to leave the N material and flow through the P material to the drain terminal. Since the conductivity of the channel is enhanced by the bias being applied to the gate, this semiconductor device is known as an enhancement mode MOSFET. Unlike the standard FET device, this transistor must be biased to conduct current. Also, with the gate being insulated from the semiconductor material, this device has an extremely high input impedance. Here you see 4 insulated gate MOSFET devices being used to control the action of a DC motor. Due to the extremely high input impedance, the insulated gate MOSFET transistor is widely used in servo controllers. Generally, the controller will use the enhancement mode device like the one you see here. However, there are several types of MOSFET devices available, and they do not operate the same. When replacing these, or any transistor, always make sure that you are using the exact replacement for the component removed. In some situations, it is necessary to purchase the semiconductors in matching sets. Matching semiconductor devices will turn on and turn off at almost the exact same time. This is not true for unmatched sets. Unmatched sets may vary from milliseconds to microseconds in their slew rates. Next, we will examine the SCR. SCR is an acronym for Silicon Controlled Rectifier. The symbol of the SCR looks very similar to the diode symbol you studied at the beginning of this video. The one notable difference between the diode and the SCR is the gate lead. The gate is used to turn the SCR on. Notice that the SCR is constructed with 4 semiconductor blocks fused together. There are 2 blocks of P material separated by 2 blocks of N material. The cathode is connected to the N material and the anode is connected to the P material at the opposite end of the solid-state device. Also notice that the gate is attached to the P material nearest the cathode. Now let's see how the SCR works. When a positive voltage is applied to the gate lead, the PN junction between the cathode and the gate becomes forward biased, thereby turning the SCR on. Once the SCR has been triggered on, the gate voltage can be removed and the SCR will remain on. The SCR will stay on as long as the current flowing through the device remains above the SCR's latch-on current level. As you can see, the SCR will only turn on when the cathode is negative with respect to the anode and the gate lead is triggered with a positive voltage. Much like the diode, the SCR can only conduct current in one direction. The ability of the SCR to stay on after it has been triggered is referred to as latching. The SCR only requires a brief pulse of gate current to turn on. Once turned on, the gate lead has no further effects on the operation of the SCR. Due to the fact that the SCR remains on after it has been triggered, the SCR is generally operated from an AC source. Therefore, by controlling when the SCR triggers, you can actually control the current flow into the load device. This form of control is known as pulse width modulation. You will learn more about this later in this training course. Here you see a DC motor being operated from a 3-phase AC power source. This converter circuit is unidirectional in that it will only allow current to flow in one direction through the motor winding. By controlling the firing time of the SCRs, this converter can be made to control the speed of a DC motor. Using 2 converter stages like this one placed back to back will allow bidirectional control of the motor. Here you see the schematic symbol for the triac. The triac is a bidirectional thyristor which behaves like 2 inverse parallel connected SCRs using a single gate. Since the triac has the ability to conduct current in both directions, the leads can no longer be labeled anode and cathode. Therefore, they are commonly labeled as anode 1 and anode 2, or simply A1 and A2. Notice in this illustration that the top 4 semiconductor blocks form one SCR, and the bottom 4 semiconductor blocks form the second SCR. As you can see, the SCRs are connected in such a way that current will be able to flow through this device in both directions. Now let's see how the triac works. In this illustration, we have made A1 negative with respect to A2. A1 and A2 are the 2 main conducting terminals for current flow through this device. Notice that when the gate was made positive with respect to terminal A1, the PN junction between the gate and terminal A1 became forward biased. Also notice the PN junction to the left of the gate junction. It is also forward biased. These forward biased conditions allowed the current to flow through the top section of the triac. Now we have reversed polarities on terminals A1 and A2. A2 is now negative with respect to A1. By applying a positive voltage to the gate of the triac, we have forward biased the PN junctions in the bottom section of the triac, thus allowing the current to flow in the opposite direction. Notice that the top SCR has been reverse biased between the gate and A2. This reverse bias condition keeps the top part from turning on while the bottom part is conducting current. Basically, the triac is a 3-terminal AC solid-state switch that can be triggered into conduction by applying a pulse to the gate terminal. In this video, we are illustrating the main current carrying terminals as A1 and A2. In some literature and on some schematics, these terminals will be labeled as MT1 and MT2. This stands for main terminal 1 and main terminal 2. Also, there are other construction techniques which allow the triac to be triggered in one direction with a positive voltage to the gate, and in the other direction with a negative voltage to the gate. Regardless of the construction technique used, their operation will still be the same. Once the device has been triggered, it will remain on until the voltage drops below the latching current level. Therefore, in an AC circuit, the gate must be pulsed for each half cycle if the triac is to conduct an alternating current. In this portion of the video, you will learn how to test the diode, bipolar junction transistor, SCR, and triac. We will begin with the diode. As you recall, the diode is a 2-terminal device. One terminal is labeled as the cathode, and the other terminal is labeled as the anode. The cathode is the negative portion of the solid-state device, and the anode is the positive portion. The primary function of the diode is to limit current flow to one direction only. This is accomplished by causing the depletion region to disappear, as it does in the forward bias condition, or to widen as it does in the reverse bias condition.